Welcome to part 7 of the lecture on catalytic organometallics. Subject of today's are palladium-catalyzed multi-component reactions. An interesting target molecule is this ester, which can be synthesized by a palladium-catalyzed process from this iodocyclohexene with this allylic side chain plus 2 equivalents of carbon monoxide and 1 equivalent of methanol. So, as I said, we need a palladium catalyst. It is a palladium zero catalyst. Well, first step is clear what will happen. Oxidative addition reaction and a vinyl palladium halide is formed. That allyl group is in close proximity. However, a 4 exotrick cyclization generally is disfavored, and even more, a 5 endotrick process very rarely occurs at all. So, but we have carbon monoxide present, and therefore in equilibrium carbon monoxide is inserted, first coordinating to the palladium, and then the insertion step will take place. Forming an acyl palladium halide. Now the cyclization is no problem at all. Carbopalladation of that double bond as a 5 exotrick process. Will give this palladium-2 intermediate. Well, of course, a beta hydride elimination could take place. Forming the alpha-beta unsaturated carbonyl compound. Well, I think we, as usual, need a base there to trap the HX, to trap the acid, and to that we can get to the oxidation state 0 for the palladium again. By the way, the isomerization to this cyclopentadienone does not take place. Cyclopentadienones are unfavored. This is easily to be understood. this mesomeric structure resembles a conjugated cyclic 4-electron system, which should have anti-aromatic character. Yeah, so that's the reason why this is somewhat unfeasible. While, okay, you certainly know tetracyclone. You can synthesize this quite easily, and you can handle that, and it is stable. But due to sterically shielding by the aryl groups, conjugation by the aryl groups, and this is certainly one of the exceptions of a cyclopentadienone system. So, how could we prevent the formation of this as a final product? We would like to get to this final product. Well, if we have carbon monoxide in excess, best at relatively high pressure, 20 atmospheres, for instance, then the addition of another equivalent of the carbon monoxide will be faster than the beta hydride elimination. And again, an acyl palladium halide will be formed, which in the last step is then hydrolyzed, or an alcoholysis takes place with the methanol, and we will obtain A as a final product. So a typical multi-component reaction. Other examples, and all those which we will discuss today, are related to that, since all have norbornene as a very special reactant within the catalytic cycle. So, for instance, a phenyl halide plus an olefin plus norbornene will produce this type of product under palladium catalysis. Again, typical reactions as for the Heck reaction. It is a Heck type process. So, how can we explain this? So, first step, always the same. Oxidative addition, the phenyl palladium halide as reactive intermediate. So, as in a typical Heck reaction, the carbopalladation of an olefin will take place, and typically the norbornene is somewhat more reactive than other, although mono-substituted olefins. There is some strain at the norbornene double bond involved, which accelerates the addition reaction to that olefin. So, At the norbornene, you have the endophase and the exophase. Exophase is preferred. Giving rise to this intermediary palladium-2 complex. So in the sense of a Heck reaction, one would check how about the beta hydride elimination as the next step. This hydrogen is a trans hydrogen, beta hydride elimination always proceeding in a Syn fashion. So it can't eliminate in this direction. Well, okay, this one is in principle. Now it's also a trans one. It's also a trans one. Nevertheless, there is a second reason why an elimination to this position can't work. Please remember Brett rule. Forbids the formation of small bicyclic systems, bicyclo systems with an olefin at Bridget position. Well, very simple. Imagine the p orbitals which form that double bond. In that case, they would be almost perpendicular to each other, and this doesn't work. It doesn't form a double bond. Okay? So, if not an intermolecular reagent is present with which the palladium can react, well, then it's looking for some electron density, of course, intramolecular. Intramolecularly might be preferred because it is intramolecular and quite fast. Then, as we discussed at similar examples in the preceding lecture, a cyclopalladation could occur with, well, various possibilities which we will discuss soon. So, in this case, we have the less reactive olefin, but nevertheless sterically less hindered one. Well, norbornene is more reactive, but well, have a look at the surrounding, the sterically demanding surrounding of the palladium here in this case. Now the palladium, this palladium-2 complex prefers the reaction with the other olefin, and well, it terminates this multi-component reaction with a simple Heck reaction at the final stage. Yeah, well, okay. Here it is. So, related to this type of reaction and is the so-called Catellani reaction. named after Marta Catellani from Parma University. She was one of the first studying this type of processes. To my knowledge, also this reaction was studied first by Marta Catellani. Similar reactions have studied also by Armin de Meyer at Göttingen University. And the Catellani reaction, which we will now get to know in detail, was also studied by Mark Lautens, who found interesting applications. Well, what's the Catellani reaction? A highly interesting multi-component process where you have generally an aryl iodide, then some bromide or other iodide. There are often is an alkyl group or a functional alkyl group. It can also be an aryl group. You have always norbornene present, and norbornene within the Catellani reaction works as a co-catalyst although it is often not applied in catalytic amounts, but in equimolar or even in excess. But it works as a catalyst. It goes into the cycle and leaves the catalytic cycle again. Therefore, it's some kind of a template at the norbornene carbon framework. The reaction takes place. So, norbornene as a template. So, and there is some more reagent which might be some stoichiometric organometallic compound or for instance an olefin. So let's study the mechanistic features of that Catellani process first. Well, again, plus palladium 0, the aryl palladium halide, and just as outlined before, plus the norbornene, you will get this intermediate. So, in the example before, a reaction with the olefin took place. You might have the olefin here, but the reactivity must be triggered somehow. For instance, you have it in lower concentration. You can influence the outcome of a reaction, of course, by the concentration. So, and thus it is possible to tune the reaction that the intramolecular process, the formation of that 5-membered Pallada cycle, is preferred. Depending on the reaction conditions, was also a group of Marta Catellani and others who found numerous products you can selectively synthesize depending on the reaction conditions. If someone wants to follow their syntheses, one should look those reaction conditions simply up in the literature. Yeah. Well, it is possible under certain reaction conditions and maybe with special ligands to achieve such a reductive elimination and forming this strained benzocyclobutene. Or adding another aryl halide, well, let's assume with some substituent, phenyl halide with some substituent. I think we discussed that before. It has never been proven that such a palladium-2 cycle adds directly an aryl halide, becoming a palladium-4 intermediate. Yes, with an alkyl halide it is possible, the palladium-4, but it has never been proven directly that an aryl halide is directly added to the palladium. Maybe a second palladium is involved, for instance, letting this palladium-2 intermediate react with that one. And ligand exchange reaction might be in the sense of a disproportionation, as I already explained, a palladium-0 and a palladium-4. But, well, newer results, also reported by Marta Catellani and Antonio Escher-Warren, tell us that indeed a ligand exchange reaction could also produce an intermediate with 2 palladium atoms involved in one intermediate. This is a bit strange because this type of reaction is known also to proceed at the catalyst loading at 0.1%, for instance. Yeah? But nevertheless, this DFT calculation showed that a reaction pathway, mechanistic pathway, with such an intermediate could be thermodynamically favored. Well, these are the details. If you want to get to know these details, then please have a look into Marta's publication in the Journal of the American Chemical Society in 2011, 133, on page 8574. So, here a reductive elimination would take place. Well, a cyclopalladation in this case could form then a 7-membered pallada cycle. Reductive elimination could deliver such a product, or this could turn around and the palladium could attack this position. Okay? Then we have this situation. And the addition of another aryl halide through an aryl palladium halide or not, could then give such an intermediate which could undergo, depending on the reaction conditions and additional ligands, CH activation here and a cyclization there. But, and this is then a typical classical Catellani reaction, this system now is somewhat overcrowded. And remember, the carbopalladation, just as the hydroboration, is reversible. So now an elimination, a beta carbon elimination could occur the catalytic norbornene is restored. And on the other hand, in principle, such a product is formed. Well, with the palladium, they're sitting there and waiting for a reagent presenting some electron density. So, and here we could assume further reactions forming interesting products. Well, in this example, could imagine that again a 5-membered Pallada cycle is formed because we have reactive positions here. But with alkyl chains here, it is far less reactive. So, therefore, a modification. Let's start again from this intermediate, that Pallada cycle, and let us offer an alkyl halide, for instance an alkyl bromide. Now it becomes apparent why generally an aryl iodide, a iodoarene, is the starting point of the Catellani process, since the carbon iodo bond is more reactive than a carbon bromide bond. So, an alkyl halide will introduce the alkyl group here, turns around second cyclopalladation, I don't know, This must be a bromide here, of course. Second alkyl bromide. That complex sterically overcrowded. Norbornene restored. So, and for instance, imagine that we have in stoichiometric amount an organometallic reagent in there. For instance, a boronic acid. Then transmetallation. Will transfer this aryl group or an alkyl group sitting at that stoichiometric metal, organometallic reagent, and reductive elimination would form a biaryl system like that. Or again, having that less reactive olefin present, then this would be the final product of the Catellani process. So, just as a brief exercise, please write down the structure of the product if these ingredients will react. Well, this is an early procedure with 10% Palladium-Catalyzed, potassium carbonate as a base, and well, dimethyl acid amide. Well, seems to work at room temperature to my surprise, and 30 hours reaction time. Please, as an exercise, try to figure out what is the product of a Catellani process. Should be fairly easy. You should simply have a look, well, at that general scheme. So the task was simply to put together all those ingredients in such a manner that something like that will be formed, and this means that as the final product of this Catellani process, we should anticipate the formation of this structure, and this is indeed the case, certainly under optimized reaction conditions, isolated with a 93% yield. Next example. 4-iodoanisole, 6 equivalents of norbornene, this 4-bromobutyric acid ester was applied with 10 equivalents, and with isopropyl boronic acid as the additional organometallic reagent. While we can speculate why 10 equivalents of that? Well, okay. Maybe in this case you need some excess of that, since if sometimes the palladium-0 will also react with that alkyl halide first. Okay, not a big deal. Beta hydride elimination will take place, forming an olefin. Well, and that means this reagent is somewhat consumed unproductively in the sense of a Catellani process. Okay, that's how I interpret those that stoichiometry. Well, this aryl group is introduced in the first few steps. Then the ortho position is functionalized at the norbornene template. The norbornene template is restored, and then we should have this intermediate. By the way, the reaction conditions, well, palladium acetate, 10%, and triphenylphosphine, 20%, cesium carbonate, 5 equivalents, (20 hours) reflux in acetonitrile, DMPU, 95 to 5. Well, okay, these are details, and well, simply because those research groups have optimized every single example, I think. So, now, on the final stage of a reaction, it will react with the organometallic species here, stoichiometric organometallic species. Well, what will happen? That isopropyl group will be transferred. And if someone thinks that the isopropyl group is then, well, transferred in the sense of a CC bond formation, is wrong. These processes are indeed possible, but you need special ligands, bidentate phosphine ligands with a huge bite angle, yeah, that the beta hydride elimination is slowed down. In this case, with simple phosphine ligands, triphenylphosphine ligands, the beta hydride elimination is preferred to the reductive elimination. So, and that means propene will eliminate antihydridopalladium aryl complex is formed, and now the reductive elimination will give the final product, this one. So, is this interesting to have a hydrogen here? Well, it is. Imagine, now you have a 3 times matter substituted product. It's not that easy to synthesize that normally step by step. And here it is indeed a domino process, just one preparative step to get from here to there. Well, yield obtained, as I said, of course optimized 89%. Another 3 examples, modifications of the Catellani process, all from Lauten's group, I think at Toronto University. Norbornene, 7 equivalents. Well, then again, base and palladium acetate in catalytic amounts. What happens as the main process? Oxidative addition to that aryl iodo bond. Then next reaction with the norbornene and a cyclopalladation, which might take place to this or to that position. For the product which is in focus, we need the cyclopalladation to this position, since the final product is formed in just 47% yield. You can assume that while some side reactions occur with the cyclopalladation with the other residue selectivity. So, well, carbopalladation will form this intermediate, cyclopalladation, then we have that 5-membered Pallada cycle and in close proximity already that alkyl halide. Okay? So, well, I should draw another intermediate. I hope that this one is correct. So 2 CH2 groups here before that acrylic moiety is introduced. Oxidative addition to the palladium-4 intermediate. Then reductive elimination connecting this carbon to that one. Right? So, what is formed? 5-membered ring. 1, 2, 3, 4, 5. A dihydro benzofuran CH2, CH2, and then the acrylic ester moiety. Well, under the right reaction conditions, yes, and it is higher temperature, microwave, 180 degrees. The retro-carbopalladation, the beta-carbo elimination already occurs. The norbornene is restored, and then the palladium will sit at this position, at the peri position. Let's count. 1, 2, 3, 4, 5, 6 positions. That means a 6-exo trig process will occur. So, and we should keep in mind the stereoselectivity of that process. So, Syn addition process. Okay, the whole process since, yeah, well, okay. There is already a chiral center in there. And the chiral information, it keeps somewhat its chiral information within that oxidative addition step of the palladium-2 intermediate. Yeah. Well, okay. Let us assume that we have here the following stereo information. This is certainly a Syn addition with aryl group and the palladium approaching the trans olefin from the same side. Then a rotation around that single bond of this intermediate must occur, that the beta hydride elimination can occur. And this then explains the stereochemical outcome of that process. As this one. As I said, well, a 47% yield was obtained for this reaction. Next example. This is the aryl iodide. Now the alkyl halide is functionalized with this interesting indole moiety, 1 to 2, a norbornene again, 2 equivalents, palladium 0, base, and so on, as usual. We skip the details. Meanwhile, it should be clear that this should be an intermediate if after addition to the norbornene system, the first CH activation takes place here. In this example, it will actually don't matter. Since if you have a CH activation on that side, you will then introduce that moiety through reaction with the alkyl bromide first. And then the CH activation at the other position will take place. The outcome of the reaction is anyway the same. So, palladium-4 intermediate, CC bond formation here. Now, cyclopalladation to the other ortho position. And, yeah, well, okay, maybe I should draw that. Cyclopalladation here, then adding that bromoalkyl substituted indole leaving the template moiety will form this one. And now again, that electrophilic palladium-2 is waiting for some electron density to coordinate to, well, and the next position which is offered is that one, the 2 position of the indole ring system. 1, 2, 3, 4, 5, 6. So a 7-membered Pallada cycle, reductive elimination, will connect this position to that one. Well, okay, let's draw the resulting structure. So, and between the nitrogen and that carbon, we have 3 methylene groups. That should be the result, which has been isolated with a 62% yield. As you see, it's really fascinating how complicated the structures might be which are synthesized by a single preparative step, by this marvelous reaction. Last example. Again, with indole moiety. And here, then, as second ingredient, despite all the other stuff, the palladium chloride a ligand called TFP. It's this one. 3 furanyl units at the phosphine, rather electron-rich one, cesium carbonate, and of course norbornene. So those who would prefer to do that as an exercise at home should not listen to what I'm now telling. Well, okay. Norbornene is introduced here to the open ortho position. The CH activation should occur. That means the connection to that carbon will occur from this position. So let's see. The palladium bromide will, after the extrusion of the norbornene template, the palladium bromide will be sitting here, and now, yes, right, 3 CH2 units, then the alkyne. This is the most reactive, electron-rich functional group within this intermediate. So a syn carbopalladation at that alkyne will occur. 1, 2, 3, 4, 5, 6. A 6-exo-Dyck process. And again, the 2 position of the norbornene moiety will then be the site of choice for terminating that process. 1, 2, 3, 4, 5, 6, 7. 7-membered ring will be formed. Ah, well, this is a nitrogen. I hope you know that. Is that right? It should be. Oh, the arrow group is missing here. So, depending on the arrow group, 70 to 90% are obtained. Well, okay. I hope you found the Catellani reaction interesting. Greetings to Parma, to Marta Catellani, and thank you for listening.